absolutely wonderful to be here, and it's great to see some familiar faces. So welcome back. I'm pleased to be here. Believe it or not, I was a first-year teacher a little while ago, incoming teacher. It's actually quite a while ago. So I do remember any sort of anxiety I had about those first-year jitters, and having this MPT on top of that, I can't imagine that that adds more stress and anxiety to an already challenging time period in your professional life. I do mention that because I'm sure that one of the challenges is our mindset. And just before we actually get going formally, I just want to mention that in my experience teaching students in the high school and in some elementary schools, what I do find is that mindset often limits us. And when we're very anxious and worried about performing on a particular assessment, that sometimes that blocks our thinking and doesn't allow us to really reach our potential. One of the strategies that we often use, it's a pedagogical approach, is to try to choose gratitude in our thinking. And there was some study, there was a study done several years ago, I think it was through the University of Chicago, that looked at where stress and math anxiety in particular is perceived in the brain. And what was discovered through these functional MRIs is that the area where the stress and anxiety happened was the exact same spot where gratitude was experienced. And the wonderful thing about this is that that particular area of the brain could only do one thing at once. So if it's busy thinking about something to be thankful for, grateful for, then it really can't experience that anxiety at the same time. So it's something that we use with our students. I know it's not directly related, but perhaps in your teaching practice, that's something that you can take forward and share with your students. We've had great success with that. So at this challenging point where you guys are preparing to ace this test, that's something that you might want to consider, just something to offer. Before we get going, I just want to share with you, because I'm afraid I might forget. Remember we said I started teaching a while ago? It's that brain. I'm afraid I might forget to mention it later. So I just want to show you some resources that I've pulled together. And I know that Ian is going to send these in the follow-up email. But just in case we don't all stay online the whole time, I thought it was probably best that I show you them now. So I'm not asking that you actually go in and look at these now. I just want to help you navigate them so that after our session today, if you're looking for next steps and maybe some further practice to support your learning, you'll know where you could possibly go. So one of the things that Ian is eventually going to share is a link to Desmos. And I've actually created a Math for Beginning Teachers Desmos account. And so once you click that link and register, it will give you access to all of these different activities. So if you are considering a particular topic and you're like, you know what, I don't even know where to get started with that. I don't understand how that really comes together, how that concept is formed. These are more formative types of investigations. So they're designed to help you learn and really truly understand a concept. Ian eventually is also going to provide you with some details about how to sign up for a Delta Math account that I also created for the participants here today. And the focus of this particular account and list of activities is different than the Desmos. So this is really just about practicing. So if you feel like you understand a concept, but you're like, I need to practice that to get a little bit more proficient, to increase my fluency with that mathematical concept, then the Delta Math is what you'll do. And you'll notice all across the top here are the different topics that I've created little tasks for that you could use to practice. And you can keep going with those. The great thing about these Delta Math is that they will provide for you immediate feedback, and it all shows solutions. So if you get it wrong, you can see the solution and it shows you a real breakdown, and it's a real intuitive, it's not like a trick sort of way to do math. It's the true understanding of how to do math. And some of them are guided and interactive. So that's just something to consider later on. I mention it now, as I said, just on the off chance that I forget to later and you guys get these links and be like, what on earth is that about? So now you know. So in terms of getting started, Ian and I think that maybe the best way to do this is to have a Padlet. So Ian, are you able to send that link in the chat? That would be wonderful. So in the chat, Ian is placing a link to this Padlet, and you'll notice that we've already placed a couple of topics here. So what we're hoping that you will do is read through these and give 5 stars rating to any type of topic that you feel like you would like to look at today. If there is some particular topic that you feel is missing, that you're like, I really want to see that instead, then please take a look at the bottom right. You'll see a little pink plus sign. Also, feel free to add a topic there. So this will help to give us just a little bit of direction in terms of where we might want to start our conversation today. And I'll kind of have a look here, give another minute or so. So linear relations, equations, Pythagorean theorem. I'm just jotting these down. Okay. And slope. Okay. Oh. This is exciting. It's changing as I'm watching. Okay, so it's looking like Pythagorean theorem is number 1 in measurement. And then we're looking at linear relations and some slope.
Just a reminder, if someone's added, as we see long division is being added there, that anyone can also rate that one.
Long division. Are they really putting long division on this? Oh, wow. Okay, we can take a look at that. Okay.
Yeah, they're putting long division on it. It's a part of a section of the test is like no calculators.
Right.
So we have to do like, I know in the practice test, it was long division with like multiple digit numbers. So that's what we'll have to do for one.
Okay. Sure. All right. So we can, hopefully we'll get to that one as well. I'm sorry, you know, I mean, I know that it's on there. It always surprises me though, sometimes what's on these standardized tests. Okay, no problem. So are we okay with us kind of taking what we have? Oh, I'm seeing some more come in here. Maybe another 30 seconds, and then I think we'll take what we have here and get going, because I know your time is valuable and we want to get through as many of these ideas as we can. All right. And we see interior and exterior angle sums as well too, of polygons and stuff. Okay, fantastic. There's some great Desmos activities about those too. Okay. Yes, there are, and they actually have some dynamic geometry videos embedded right in it. Is Courtney, were you asking about that one? Okay, because I'm looking at that one and I'm hoping we get to it, but if it's a rate of 1, if we don't, be sure to check those out on the Desmos, okay?
Okay, awesome, thank you.
You're welcome. Okay, so how about we go ahead and start with Pythagorean theorem, and then we look at slope, rate of change, linear relations, because they're actually tied together quite closely, and then equations in the algebra, and then try to make it through as much as we can. Does that sound okay, team? Yeah? Okay, perfect. All right, so Pythagorean theorem is what we said. So I am going to share my screen with you. And this is just a little OneNote that I created just to try to, you know, I basically pulled together some of my stuff that we do in grade 9, because I think that that's stuff that will help us. Unfortunately, I'm not able to share the OneNote because I can't share it outside of my organization, which was a little bit of a bummer for me. When I made it, I had anticipated sharing it with you. So I apologize that I cannot do that. Nonetheless, if there's a couple of key files that you feel like you would need, I can definitely try to track those down for you and send them along. So when we,
Yeah, sorry, just a reminder that, of course, that will be in the recording. So this will be on the screen because you're sharing your screen. Folks will be able to see that though, but they just can't share the live version of it.
Okay, perfect. Thank you, Ian. In terms of the people who did upvote Pythagorean theorem and measurement, was it Pythagorean theorem that we were really most concerned with? I did mention that because I found that that was something that people in the past had had questions about. Okay, so I'm not seeing any. So I'll start with that and then we can go from there. So Pythagorean theorem is just a way that we can use to find the unknown side lengths of right triangles. Now, something that I think is really important for us to recognize that if the triangle is not a right triangle, if it does not have a 90 degrees, then Pythagorean theorem cannot be used to find an unknown side length. Now, I'm just thinking back to when, I have done EQAO with my students in grade 9. And I know sometimes in those EQAO tests, the sneaky guys, they put in their triangle that is not identified as a right triangle, and they put a possible answer as one that would be used from Pythagorean theorem. So please just be mindful of that. If it's anything the same, that might be something to be watchful about. So what you're going to notice is that we do have a right triangle there. I've tried to draw it for you. And one of the really key things is the side that we are identifying as the hypotenuse. Now, what I find personally, when people are looking at this and thinking about this, identifying that hypotenuse is actually one of the most important things. Because when we don't do that, it tends to get a little bit more mixed up. So the easiest way to identify the hypotenuse is to know that it's directly across from that right angle. And oftentimes what I get my students to do is to actually highlight that another color. It sounds like a really silly thing to do, but if you're in any way a visual learner, that will really help to kind of key in to what your next step needs to be. Now, what Pythagoras said about right triangles is basically that the area on this hypotenuse, so there's my triangle drawn again. He said that the area on the longest side, which is the hypotenuse, was actually equal to the area on the other two sides added together. Now, I know that we may have seen a squared plus b squared equals c squared, which is awesome. Okay, that's the way I learned it, to be honest with you, back when I was in school. The challenge with just thinking about it in that way is that sometimes when they tweak things around, that approach breaks down if we don't understand why it's working the way it is. And so that's why I am going to just show you quickly this area model in the hope that it will prevent you from getting mixed up in any way. So what we're going to notice is that the area on the hypotenuse is actually equal to these two areas here added together. And by the way, guys, it doesn't matter what shape is on here. I've drawn squares because that's the traditional way that we see Pythagorean theorem, but it could be any shape. It could be a half circle. It could be anything, okay? It's always the area on the hypotenuse is equal to the two areas added together. So I want to use a diagrammatic approach in order to work this through. Now, that's something that secondary teachers have been learning more and more from our elementary colleagues who seem to be experts in this respect. When I learned mathematics way back when and continue to learn, it's always like in a really symbolic way. So when I talked about a squared plus b squared plus c squared, that's like symbolic, but there's not always great understanding. Our elementary colleagues have shown us secondary teachers that actually drawing a picture is lots of times way, way more effective. So if we want to take a look at the example that we have here, one of the first things I want to do is draw a highlighted section on my hypotenuse so that I really, really remember that I am keeping my eye on that hypotenuse. Okay, my Wi-Fi is a bit laggy here. My apologies. I'm highlighting this hypotenuse, which I'm calling C. Now, the next thing I'm going to do with that is I'm actually going to draw my squares on each of the sides of my triangle. Oh, good. It's catching up with me. So I've got my two little squares and my big square. And what I'm going to do is just really find the area of the squares. It's that simple. So notice that it is a square. So I know that one side, which is also the side length of the triangle, is 7. And if this is a square, then all of the other sides on that square would also be 7 meters. When I want to find the area of that, any ideas how we would find the area of that little square? This little square right here?
Yeah,
Yeah.
great. People are popping that into the chat.
Perfect. Yep.
Great.
I'm seeing that. Fantastic. Length times width. You've got it. So in this case, since both the length and the width are the same, I've got 7 times 7, which is 49. Similarly, down here with our other smaller square, the area there is 10 times 10, of course, which is 100. So what Pythagoras told us is that the area on the big side, the area on the hypotenuse, is always equal to these two areas added together. So since the side length of this unknown side is C, notice that would be C as well, the other side. And so the area there, which is C squared, would just basically be the two areas added together. So it's like 49, which is the area on one of the sides, plus 100, which was the area on the other side. So we'd have the C squared equals 149. So fantastic. We found the area, but we noticed that the question actually said, calculate the length of the missing side. So it's not really the area we were looking for. It was the length of the side of that square. So any ideas how we would undo this square to actually find out what the length, what two numbers multiplied together would give us the 149? What could we use for that?
Can I talk?
Yeah.
So
Sounds
we can
good.
root 149.
Yep. Fantastic. So we're actually going to, like you said, square root of both sides, square. And so I'm getting approximately 12.2 meters as my answer. So you'll notice that that's a way to do it diagrammatically. If I had wanted to do C squared equals A squared plus B squared, we can, of course, do it that way. The C squared is what we don't know. One of our side lengths was 7 squared. The other side length was 10. You'll notice that as I write this out, we're getting the exact same answer. So I'm just writing it out in a slightly different way there on the right. And C equals approximately 12.2 meters. Okay, so either option works. And as I mentioned, I wanted to show you this diagrammatic approach because I think in particular for the next example that we're going to look at together, that's where this diagrammatic approach is really helpful. Okay, any wonderings about what we've just done here?
Just pop those into the chat if you've got a question or a wondering.
Can Pythagorean theorem be used with triangular prisms? Sometimes with triangular prisms, the Pythagorean theorem might be used to find the height of one of the prisms. So I'm going to just over here at the side here, let me see if I can draw it. Sometimes, so if this is a triangular prism, are we okay that that's, whoopsie daisy here, let me see here. I'm not a great artist, but oh, triangular pyramid. Oh, triangular prism. Sorry, you said prism. I thought pyramid. Okay, let me do the triangular prism. Okay, so a prism, of course, means that both the top and the bottom are parallel to one another, and that the top and the bottom are the same shape. Are we okay with that? And you did ask about a prism rather than a pyramid, correct? Yeah. So in terms of finding triangular prisms, I'm assuming you're talking about volume of that? Yes. So in terms of finding the volume of a triangular prism like this, of course, the volume of any prism is basically area of the base times the height. So if we needed in some way to find the height here, okay, to find this area of the base. So for a triangle, the area of this base, which is the triangle, would be base times height divided by 2, times the height would be this long side lengths that connect the two congruent tops and bottoms. So if in the situation such as this, we needed to find the height of this, let me draw it in with red. So if I needed to find that height and wasn't provided with it, then yes, I might need to use Pythagorean theorem to find this height or this side length. Does that make sense? So it would be an embedded application of Pythagorean theorem, and that would definitely be like a more thinking style question. What I think that this indicates that we should look at, notice that in the situation that we're talking about here, this height that we would maybe want to find in this particular base for this triangular prism, notice that this particular side that I'm highlighting with my cursor would not have been the hypotenuse of that triangle. So I think we definitely need to look at the situation where Pythagorean theorem is used when the unknown side is not the hypotenuse. Is that fair? So I'm going to scroll down here, and I have created one just like that, because that is something I think that is very common that we probably do need to look at here. So once again, as we usually do, I want to highlight my hypotenuse, and which side would be, you're welcome, which side would be the hypotenuse in this particular triangle? Would be the X, the 25, or the 9? Awesome, 25, because it's directly across from our right angle. So I'm highlighting that just so I don't forget. And honestly, guys, if I had $1 for every time somebody forgot to recognize which side was the hypotenuse, I would actually be retired with a villa in the south of France right now. I wouldn't, I would still be doing this because I love this, but I would be in the south of France. Okay, so we have, I'm going to draw my big squares on here because that helps me to keep track of what's really happening. And just like before, I am going to find the areas of each of these squares that I've created on the sides of my triangle. So just like before, so that would be 25 times 25, which is 625. I think you can check it to make sure I didn't make any mistakes there. Our other one is 9 times 9, which is 81. And now this is where it becomes really important to think about what Pythagoras was really telling us. Pythagoras, and actually there's a whole historical thing with Pythagoras, right? There's really a rumor that it was a woman that worked with Pythagoras who came up with this, and but he took credit for it. But now we're learning that there were other cultures that actually came up with this first. So we're calling it Pythagorean theorem, but don't hold your hat, because I think that's going to change in the next couple of years as we come to recognize other ways of knowing a little bit better. Anyways, that was an aside, my apologies, but it had to be mentioned. So we take a look at this and we notice that the side that we highlighted, we already knew. So we knew that the hypotenuse was the longest side in the triangle. And we knew that Pythagoras, or somebody there in his office, indicated that the other two areas would add to give this big area. But you'll notice this time we actually have the big area and we don't know one of the smaller areas. So if I want to find one of these smaller areas, which I'm going to call x squared, and I know that the two small ones add to give the big one, what would I do with the big one and one of the small ones to get the other smaller one? What do we think?
Subtract it.
Yeah, absolutely. So we would take the 625, the big area on the hypotenuse, we would subtract the other one. And what do we get from that? So that's 544, which you've already told me in there, I see. And now, of course, we'll take the square root of both sides and we'll get approximately
24 something.
Yeah, 23.3. 23.3, and I guess that was centimeters. Okay, and that would be our answer. Now, if you remember, we said that the other way, the more traditional way, I guess, is that we would use this c squared equals a squared plus b squared. Where I find people make mistakes is they just automatically think that whatever is missing goes in the c squared spot. Okay, and that's where this little formula kind of has its downfall. We need to remember that in this case, the C, or the hypotenuse, which is what C is actually standing for, was actually given. So we would have 9 squared plus, I guess, B squared. In this case, it's really X. And notice that when we do this type of thing, we get a situation where we have a simple equation. And then if we wanted to solve, we would subtract 81 from both sides. And we'd end up with b squared equals 544, and we would go ahead and solve. So I'm writing it out in using the other approach. If that's something that you prefer, obviously you're going to do what makes most sense to you. But if you're at all unsure, I really do think that using the diagrammatic approach will help to prevent any errors and misunderstandings that you might experience later on. Okay. Any wonderings about that? If you can pop that into the chat, anything you wanted me to clarify relating that. The other great thing about highlighting that hypotenuse is that when you go to highlight it, if you can't find it, then you know, hey, this is not a Pythagorean theorem situation. I cannot use Pythagorean theorem here. So it's just a real way to hold ourselves accountable to make sure we're using it in the appropriate situation. Okay,
Not seen any
anything?
wonderings in the chat there, so.
Okay,
Yep.
fair enough, fair enough. Okay, shall we go ahead? Actually, I can show one more. I don't think we need to do this one unless you really want me to, but it's maybe a bit more of an idea of where you would apply this. This is just something I give to my grade 9s. You know, the silly party hat made of a cone, determine the height of the cone. What we notice, and this kind of ties into the cone idea that you asked about triangular prisms, but this is very similar type of application structure that we might use here. Notice if I want to find the height of the cone, that's the distance from the very tip of the top of the party hat down to the very center of the base. So in this type of situation, if we wanted to find volume, it's the same thing as the volume of a cylinder, which is pi r squared. So this is like area of a circle times the height of the cone. Okay, that's where that comes from in the formula. And anytime we have a cone, it's actually a third of that. So if I had a cylinder and I had a cone, I could actually fill up 3 of the ice cream cones, and 3 of those would fit inside a cylinder that had the same circular base. Okay, and that's why the formula is actually pi r squared h, which is the volume of a cone, divided by 3, because it takes 3 of those cones to fill up the cylinder. Okay, so that's all makes sense, and there's a reason why the formulas are as they are. So in this sort of scenario, if I wanted to substitute in here, I was implying that this 10 centimeter represented the diameter of this cone. So what would we need to do with that 10 in order to be able to find the radius that clearly we need?
So it's half, it's 5, right?
Yep. So you're absolutely right. So we would get 5 centimeters. So we would know to put that in here. So we would take our 5 centimeters, plop it in for the radius. But of course, we'll notice that this diagram is not providing us with the height. It's providing us with what we call the slant height of the cone. So we would actually need in this situation, here's the great application of Pythagorean theorem, to find that height. So I could actually kind of decompose this a little bit and hope to make a bit of sense to it. You already told me that 5 centimeters represented the length of the radius, 13 centimeters is the slant height, and of course, the height of the cone would be that unknown side length in that triangle that I kind of pulled out of that 3-dimensional shape. So you'll notice it is a right triangle simply because whenever we calculate height it's always perpendicular or at right angles at 90 degrees to the base. And so we know for certain that this would be a right angle in here. And so we know that this little triangle that we pull out of that and use for problem solving is the right one. And therefore, we know that Pythagorean theorem could be used. Okay, so we would repeat that process. And then once we had that height, we can put that measure into our formula. We can put the radius into the formula, and we could go ahead and calculate the volume of that cone, if that's what we wanted to find. Oh, it was just determining the height. My apologies. I guess we're not determining the volume, but you could, okay, if it were a similarly constructed question that asked you to find volume. I kind of think that's where I was going because I was doing that with my grade 9s the other day. Okay, is that okay with everybody? Does anybody feel like they would like us to go through how to find that volume, or do we want to move on to our linear relationships?
Can I solve it?
Okay, go ahead. Do you want to?
Okay.
Okay.
13 square equal 5 square plus h square, which is like, if we move it like once, so 13 square is gonna be 169 subtract 25 equal h square, which is 144 equal h square, and we made root square of 144. I believe it's like 12 something, I'm not sure.
Okay, so this was part here. So you did the 13 times 13, 169, 5 times 5, which was 25, yes?
Yeah.
And then your h squared was equal to, you did 169 minus 25, I think, yes?
It's 144, yeah.
Okay, so then the square root of 144 is 12. So we'd have height equals 12, so it would be 12 centimeters. Whoops. So once we had the 12 centimeters in our cone, of course, we could go back and plop that into the formula. Are we comfortable with how to evaluate like the r squared and this part of a formula? Yeah. Okay, perfect. All right, you guys seem to be pretty good at that. Fantastic. All right, so if you guys are okay with it, I think that maybe we go ahead and look at some linear relationships. And that can also help us to deal with rates of change and whatnot. Okay, so let me just pull out of here for a second. And I'm going to go back into visual patterns here. And then I know we wanted to look at slope as well. I think that starting with visual patterns will actually be a good segue into slope. So I want to show you this here. And as I've said, you know, I've learned so much from my elementary colleagues over the years. And this is one of the things I realized when working with them, is that having an actual visual pattern really makes the math much more accessible. So I know that I could just give you an equation and a table of values to show you a linear relationship. I think that actually having a look at this particular linear pattern, a visual pattern, helps. So you'll notice in the upper left here, I just created a pattern, and this step 1 actually involves all 5 of these tiles. One of the reasons that I actually have colored them differently is simply because I wanted us to make a little bit of, to pull something from this, and you'll see in a minute exactly what it is I want to pull from it. So when I'm trying to describe this linear pattern, sometimes people like to use X for the first column and Y for the second column. So basically the independent variable as X and the dependent variable as Y. Now keep in mind that those are kind of random letters that are used, but we could use all sorts of other letters too. Some people are like, no, I'd rather use something that's more intuitive, and they might use N for step number and T for number of tiles. I'm mentioning both of these because I really want you to see that the letters we choose are just like placeholders. They are variables because they change. Okay, and we're not tied to anything in particular. If that confuses you, then choose one of them and go with it and don't worry about, everything else I said. Okay. But I think it's important for us to recognize that. So I'm going to put step 1, 2, 3, and 4 in here. And basically we can just look at the pattern that's here and fill in the number of tiles. For step number 1, I'm going to notice that there are 5 tiles because I had 1, 2, 3, 4, 5. For step number 2, of course, we have 7 tiles. Step number 3, I had 3, 4, 5, 6, 7, 8, 9 tiles. So I'm just basically counting these. Now, if I were to extend my visual pattern, extend my picture to the right and create a step 4, how many tiles would you anticipate would be in step 4?
Pop your answers into the chat there, please.
11 is correct. And can somebody describe how they figured out that 11 would be correct? Find the first difference. Woohoo! We got even first differences coming here. Fantastic. So first differences, for those of you who aren't sure, is another column that we can add onto this table of values where we subtract the y values. We can also notice those first differences by asking ourselves, what is it that we're adding each step to get the next subsequent step in our pattern? So we'll notice that we're adding 2 each time we go up 1 step. Okay, that's going to be really important later as we talk about slope. I also want to mention back here at step 0. Now I know in this text, a step 0 is like, it's a pattern. How can we have a step 0? So we're trying to extend our thinking a little bit more abstractly. If we had a step 0, I'm going to write it in here. So if I had a step 0 out to the left here, what kind of tiles would be in that step 0? How many tiles would be there? And what would they look like? So we're seeing 3 tiles, you got it. And we're noticing the 3 tiles would actually be the 3 red tiles. Okay, so we would kind of be going backwards here, or we would think, what is it plus 2? That would give us our 5. And of course, our answer is 3. So we're using that idea that we're going up by 2 each time. The fact that we're going up by 2 each time is what we often call the multiplier. And we're going to see how that works down here because it's really going to help determine the equation or the rule that can actually be used to draw this pattern. So what I want to do with us here, and I'm going to do this for us just for the sake of time, I'm going to take this table of values and I'm going to plop it onto a graph. Okay, so that you can see the connections between the picture, the table of values, and the actual graph that's created. So you'll notice that I put step number down here because it was like our X position. It was our independent variable. I put number of tiles here because it was like our Y, our vertical Y to the sky, right? The Y goes up and down. And now I'm just going to plop in the data. So first 0 was 3. So you'll notice that is right there where I've got that red dot. For step 1, I had 5 tiles, so I can plop that on there too. For step 2, I had 7 tiles. Step 3, I have 9. Step 4, you guys told me we would have 11. So what you're going to notice is that when it's going up by the same amount each time, I'm creating a linear relationship. I want you to notice that if I were to draw in a line here, I'm going to use a dashed line because it's discrete data. Are you guys okay with what I mean by discrete data? Okay, so like there's no in-between numbers. I don't have half a tile, so it's not continuous. So I use a dashed line to show the fact that it's discrete data. If I wanted to look at this and figure out what the slope of the line was, do you guys remember what the formula for slope is? Also known as rate of change.
Rise over run.
Yeah, so it's the same thing as rise over run, and I want you to see something super cool here. If we take any 2 points on this line that we've constructed, and we try to find the rise and then the run, so regardless of the 2 points that we use, We find the rise and divide it by the run. Notice in this scenario, we are always going to have 2 up, 1 over, 2 up, 1 over, regardless of the points that we use. So it was always going to be 2 over 1 or just simply 2. So that's really about what slope is. It's how much is a pattern increasing each time. It's going up by 2 with every step. That's slope. We can see that in our table of values. We can see that in our line. We call that the multiplier sometimes. We can also call it the slope. We call it sometimes the multiplier. So I'm going to put slash here, slope, because you might not want to call it the multiplier. And so our slope is 2 here. Now, our initial value, EQAO tests tend to call this spot where our graph starts, also called the vertical intercept or the y-intercept. They tend to call that the initial value. That's why I'm using that terminology in case they use that on your MPT. What would the initial value be for this relationship? It would be 3. You got it, or 0, 3. I'm noticing in the chat that we mentioned that this rise and run, somebody also said y2 minus y1 over x2 minus x1. That works as well. And that's a formula that you could plot ordered pairs into and just do the calculation. We are basically doing the same thing from a more diagrammatic way. So calculating how much does it change in the vertical direction versus the horizontal direction. And if we wanted to, we could actually use this formula as well. Would it be helpful for us to choose some points and show how this formula can be used too, for those who prefer that? Yes. Okay. So we're going to do that. I'm going to do that in just a moment. Let's just get this rule or equation out of the way, and then we'll look at that. All right. Oh, sorry. Was that a... Oh, I thought I had a question. All right. So if I wanted to create some sort of an equation or a rule, basically there's a couple ways we can think about it. We can think about what do we do with this, each of these X values in order to get the Y values. So what we're going to notice is that if we take our X value or step number and we double it and then add 3, we're going to get to each of these Y values. So watch this. If I take the 1, I go 1 times 2, which is 2, plus 3 gives me 5. Let me write that in. And I'll show you an easier way to get this. So 1 times 2 plus 3 would give us 5. If I took 2 times 2 plus 3, that would give me 4 plus 3 is 7. We okay with that? And similarly, if we followed through for each of these, if I had our 3 times 2, which is 6, plus 3 would give me 9. So lots of times we'll start with students just looking at these and just trying to brainstorm patterns, but I know that that's not necessarily a very efficient way to get our answers. The other way to do it is to notice here that the number that we are multiplying our X value or N variable, whatever you want to call it, by, is the amount that the pattern is increasing each time, or what we called our multiplier. That's the reason we called it our multiplier, because in our rule, this increase, this slope, which we're calling multiplier, is what we multiply our independent variable by. So the number of tiles would be 2 times, I'm going to put N, which is the step number. And then we're going to add, notice 3 is being added each time. And notice that's the 3 that we started with. We always had this constant of 3, right? And you'll notice that we added 2. Now here we added 2 times 2. And now here we added 3 times 2. And when you guys extended this one, you had 4 times 2. So I'm hoping that you can start to see how this comes together. So if you're able to identify the slope or the multiplier, you'll notice that that multiplier actually is the thing that multiplies by the independent variable. This initial value, basically, which is like our y-intercept, is where our pattern starts. And that's always the number or constant that's added on the end. For those of you who have looked into this a little bit more deeply, you've probably seen something that looked like y equals mx plus b form. Is that something that people are familiar with? Notice that the fact that there's an m, that's generally the way the curriculum is written. M stands, we use it to stand for multiplier. Okay, that is the slope. And that's one of the reasons why we call this the multiplier, because whatever that increase is, whether you get it from your table of values or whether you get it from your rise over your run in your graph, that's always the value that's multiplied in here. Whereas the B, which is the vertical or y-intercept, also called the initial value, is where our pattern starts on the y-axis. It's also the value that's attached to 0 in our table of values, because notice 0, 3 is clearly this point, 0, 3, that is on our graph. So you mentioned that you wanted to use that change in y over change in x. You might have also seen this written as delta y over delta x using the Greek letter delta, which means change. So you may have seen that written in there. So we could really choose any points that lie on this graph and use this formula, and it will give us the slope, because the fact that this is a linear relationship means that it doesn't increase at different rates anywhere along it. So it doesn't matter which points I use, I'm always going to get the same answer along it. Does that make sense to everybody? Because it's a line. That's one of the characteristics of a line. So let's choose some points that are a little further apart, okay? So I'm going to choose the point 2, 7, and I'm going to choose the point 4, 11. Let me highlight those so we know which ones we're going to use for this particular formula that you mentioned down here. So basically what this formula does is it just, helps you make calculations to figure out what the rise and the run are. So I'm going to draw in some new arrows, a new triangle to get to those 2 points. And notice the rise. Can we notice that that's just the vertical distance, the up and down distance? So that's another way of saying that it's the change in the y coordinates. So a change in the y coordinates or a difference in the y coordinates, I could simply get by subtracting my y coordinates. So if I wanted to figure out how tall this was, well, this is 11 up here. This is a vertical height of 7. Are we okay that for that particular scenario, it would be like 11 minus 7? And then when we're looking at the run, because it's the horizontal distance in the x distance, it's going from a distance of 2 over to a distance of 4. If I wanted to find that distance, I could simply subtract the 2 from the 4. And that's going to provide that change in x, also known as the run. So it's just a different way to kind of write down your answers. Now, the advantage of this formula too, is that if I don't give you a graph and say, here are 2 ordered pairs, find the rate of change or slope of the line that joins those, then of course this becomes more efficient because I don't have to draw my picture. Okay, but as long as we understand what the x and y coordinates are doing for us, we can work that out. So 11 minus 7 would give us our 4. 4 minus 2 is of course 2, so we would get 2 as our answer. So notice that even though we chose 2 points that were further apart, we still got the same value for slope. Let me just jot down those ordered pairs beside here. Whoops. So we had the ordered pair 4, 11 and 2, 7. Something I just want to mention. So if we didn't have the diagram here to support our thinking and we're only looking at these ordered pairs, my change in y would be my y coordinate, subtract my y coordinate. That was on the top in the numerator. My denominator is my change in my x, which is also going to give me my run, which would be 4 subtract 2. Now, here's where these little rules make us fall off if we don't really understand what we're doing. You've got to be careful if you don't have a picture that you're really comparing these 2 points in the same way. What I mean by that is this. if I'm starting here and decide to go 11 subtract 7 as I calculate my change in my y, I need to make sure I'm consistent as I subtract my x's, and therefore I would need to go 4 subtract 2. So let's pretend this is called point A and this is point B. If I take A minus B for my y's, I need to go A minus B for my x's as well. Otherwise, I'm going to mess this up. It's like, because I don't visualize it, I don't understand I'm making a mistake. So that has something I need to be mindful of. Now, also keep in mind that if I chose instead to go 7 minus 11, that's okay. As long as when I take the difference in my x, I go 2 subtract 4. And if I do that, watch what happens. 7 minus 11 would give us -4. 2 subtract 4 would give us -2. And notice the -4 divided by the -2 is still going to give us +2. Okay, so we would still get the same answer regardless of which order we want to substitute in. Basically, which one we want to call point 1 and point 2 doesn't really matter. It's irrelevant, but I need to be consistent. If I subtract my y's in one order and subtract my x's in the other, I'm going to get probably a wrong sign somewhere in there, and I'm going to get an incorrect answer. Is that okay with everybody? Do we see where we're going? So just that's a little caveat to be careful of that, okay?
Hi. Actually, a tip that one of the another tutor had given me was on the visual itself. So if you go up a little bit more, she said that you could choose any coordinates. Obviously, you chose 4, 11 and whatnot. And she says on the top of each number, just so that you don't get confused. So for example, I'm sorry, can you go down a little bit more? She said, okay, so you've chosen your y2 minus y1. So go up to number 7, number 11, and put y2 with a different color, she said, so you don't confuse yourself.
So just call this like x2, so y2 sort of thing?
Yeah, exactly. So do it that way. It's just, for me, I know that I probably will make a mistake if I don't have those consistencies in place.
That's
so
a great
I just
idea.
thought maybe to share that.
Awesome, thank you. Great idea. So labeling our points, I think that's a great something to take away. And fantastic. Anything else, guys, that we want to add here?
I just want to ask you about the point. Is it that supposed to be 211? Because you put 2.
Did I write something wrong?
Yeah.
Where?
Here, the second point. y2 minus y1. Do you see like 4 and...
Yeah, right here. I wrote 11 minus 7, yeah?
No, here in the graph. You put it 2 and 1. Supposed to be...
Oh, that's a 7.
Oh, 7. Oh, okay.
Yeah, because it's up 7 units here. Yep.
Oh, okay. I thought...
Yeah,
it's
2,
okay.
7. No, that's just my handwriting. Okay, so we had another... Oh, sorry.
No, all good, I think.
Okay. Awesome. So we had a question. Can any points be chosen to find slope? Yes. It does not matter which points we use on that linear relationship, on that line. Regardless of the point, you will get the same answer. Yep. You're welcome. Okay, so there were also slope questions. If there's nothing more with that one, let me... rate of change or slope. Let's take a look at some of those that maybe we could practice.
I'm just watching time here. We have about half an hour, just so you're
okay,
aware.
Perfect. And we still need to do solving equations, don't we? At least. Okay, so we're just going to do this. Actually, are we feeling okay about slope now, or do we want to look at some more? Okay. All right. So let's do one more for slope and then we'll move on to solving equations. Okay. Sorry. I'm just going to, this is getting a little bit, there we go. Okay. So there's lots of situations. These are often from EQAO, and this is why I chose to include these here. You are going to get some more analytic style questions, which we've already looked at by looking at that particular formula. For these styles of questions, let me see if I can make it a little bit bigger, because I think that that's a little bit hard to see. It's not letting me make it bigger. It's not, my apologies. So here's an example. Let's just try one of these together here. Here's an example where we have distance below the surface versus time. So we're dropping something into the water and just a matter of practicing rise and run. So to echo the point that was mentioned before, doesn't matter which points that we would actually use here? And the answer is no. All I would say, I mean, this one, really, any of the points are easy to use. Sometimes, however, it's difficult to read a particular point. So I wouldn't choose a point kind of in between, something that was difficult. I would make sure that I chose a point that was, from an easily readable coordinate. So in this type of situation, I don't necessarily have to start at 0, 0. I could start up here. And I could choose some other point, and I could basically find out what the rise was, find out what the run was, and then really find the slope from there. So we'll notice here, sometimes we're not going to be provided with every little tick on a graph. In this case, we'll notice that every second tick is worth 8. So we'd be expected to use some, reasoning to infer that the single tick was worth 4. So this is really going from 12 all the way up to 24. You'll notice that this rise would be from 12 up to 24. So that's a rise of 12 meters. And then we would look at the run, which would be the distance between 1.5 and, so I'm looking here from this point, which is halfway between 1 and 2. So 1.5 all the way over to 3. So that would be 1.5 minutes. And then we could go ahead and just simply divide. So 12 meters divided by 1.5 minutes. And I should be able to do that in my head, but it's been a long day and I don't want to write down the wrong answer. 8. So I got 8, and that would be meters per minute. Now, what you need to really be mindful of as you're doing these types of questions is that particularly when they're using the phrase rate of change, they really are wanting you to have your units attached to that. Slope is used interchangeably, but often in a more analytic scenario when we're looking at like y equals mx plus b, that sort of thing, they use the word slope. Rate of change is used for more application style questions. So be sure to include your units there. Keeping in mind that if you don't like this looking at the graph and these points were given, notice this 12 can be obtained by just going 24 minus 12. That's your subtraction. And of course, this was 3 minus 1.5. So the subtraction works really, really well too. I'm always just mindful that if we just understand what's happening, it's a lot easier to manage than trying to remember all these formulas. And that's why for me, I find with students that sometimes that works better for them. Oh, cool. Question about would this be direct variation? Yes. This is direct variation because the initial value, y-intercept, is 0 because it passes directly through the origin. This is an example of direct variation. If my initial value or y-intercept was not 0, like the one that I'm showing right here, can we see that the y-intercept would be 15 instead? In that sort of situation, we call that partial variation. And that's a really big thing that they put in the grade 9 EQAO math thing. And I've never, ever seen it in math anywhere else in my life. And I worked as a mathematician before I was a teacher. But anyways, you might need to know it. So direct goes directly through the origin. Partial, it doesn't. Okay, that's really just the best way to remember it. I haven't come up in many years with a better way to think about it. I think we need to, it is, I'm not sure if it is in the new curriculum. I don't know if those terminology is, but I'm actually working in the new curriculum now, and there's a lot of this same sort of stuff, though the linear relationships tend to be very similar, but we will find out. I don't know if they call it direct and partial, but I've spent 4 days on that new curriculum and it's very exciting. Looks really good so far. Okay, so maybe we can take, the origin is always the 0, yes. Origin is the point where our two axes meet and the coordinates of the origin are 0, 0. meaning 0 coordinates left or right, 0 coordinates up or down, kind of like the bullseye in the center of our Cartesian plane. Okay, so let's maybe take a look at solving some equations. And I'm going to go right to the more difficult ones. And you guys can tell me if we need to back up at all. And I've got a couple here that I thought we would try, 2-step equations, and I've tried to create them so that there are some things that we might need to be, mindful of as we do this. So I'm wondering if you guys want to jot this down, and we're going to try it together. And I'm going to try to go through in an explanation. And I'm going to try to be mindful of the thinking as we go through it. So we may have learned certain steps and tricks that you might know to make this work. Even if I explain it a slightly different way, it's not going to make your steps and tricks not work. Okay, but I just really want to make sure that you understand why what you might be doing actually works. I always find that when we do that, it really prevents us from making errors that could be problematic. Okay, so if we're looking at this particular equation, I'm going to call this A. When I'm asked to solve an equation, I am looking to isolate the variable or letter, get it by itself. And basically, what we really want to do with this is to try to undo the connections that are already there. And whenever we are solving an equation and undoing connections, you can always think about it like a teeter-totter, because the equal sign is a balance. And if I do something to one side of the teeter-totter, I have to do the exact same thing to the other side of the teeter-totter. Otherwise, I get this balance upset. Another way to think about it, once we get more complicated, is like untying a knot. When I have some knots, I have really tight knots that are closely connected, and I have looser knots. If I'm thinking about untying a knot in my necklace, I always start with the looser knots and then work my way back to the really tight knots that I work at the end. When you're thinking about it in that context, we see some connections here. We see that the -5 is connected to the D. Can you see how the D is really close to the -5? So that's like a tight connection. Whereas the subtract 3 is a little bit further from the D, so it's a looser connection. So that's the connection I'm going to try to undo first. So the one last thing we need to remember when we're solving equations, that if I'm trying to undo the connections, undo these knots, I'm always going to use the inverse operation. So if my connection or my knot is addition, say, to undo it, I would subtract. Similarly, if it was subtraction, I would add. If it was multiplication, to undo multiplication, I would divide, and vice versa. So if we take a look at this particular scenario, I noticed that the loosest connection, i.e. the one that's connected by addition subtraction, is subtract 3. If I want to undo subtract 3, to undo that connection, I would add 3. Now, the way you may have seen it is that, hey, this is subtract 3, bring it over to the other side, I will add 3. Yes, that works. I want you to see that the reason why that works is you're still putting the +3 over here, but you also, in essence, added the +3 on the left side. It just so happens that that subtract 3 and +3 make 0, and that's why we don't write it in. So we end up with -5D equals 20. Now, if I wanted to undo the connection between the -5 and the D, we notice that that connection is actually multiplying by -5. So as to undo a multiplication by -5, I would divide by -5. So we would get -5 divided by -5 is 1. So we're left with D, and then -4 is our answer. Okay, let's try one other little one here. What's the first thing? Just pop it into the chat. What's the first thing we're going to do on both sides of the equation to try to move towards the Z being isolated?
Can I talk?
Okay. Yep.
Okay. So we're gonna move 7 to other side.
Yeah.
It's gonna be -4 minus 7 equal Z over 3. So Z equal,
It's there. It's just populating. And then both sides, what would we do to both sides next?
yeah, we just divided by 3, or I just do cross multiplication. So it's
Okay.
Z equal minus 33.
Okay, so we are connecting, we are connecting the Z to the 3 by division. So I see Jazz saying we're going to multiply both sides by 3 to undo that division. That's correct. So we'll multiply by 3 and therefore multiply the other side by 3. And notice we get Z equals -9 as our answer. The other way you can think about it, if you don't want to write in the 3 on both sides, then don't. We're dividing by 3. When it comes across, it becomes multiplication. That's a trick. And I know that that's how I learned it. Just be mindful of why it's working, because sometimes it kind of breaks down. Did I write something down wrong? Oh my gosh, I added 3.
Yeah, you're wrong.
I
That is
am.
supposed to be
Yeah,
3. Yeah,
there we go. Thank you.
yeah, no problem.
Perfect. Thank you, Courtney, as well. All right. So any wonderings about that? So any other situations, sometimes we just group our like terms before we would go ahead and solve the equations. So notice here we would have our like terms, 6K and -3K. We would just need to group those like terms before we went and did exactly what we did up top. Okay. Only other thing that we probably would need to chat about is what happens if we have variables on both sides of an equation. I have a diagrammatic approach here that we could maybe just look at so that you can understand this. So this little diagram might be used to represent an equation that looks like this. So notice we've got an x plus 9 on one side. We've got a 4 plus 3 of the x's on the other side. So this might be a type of equation that you might be presented with. And notice the difference here is that we actually have the variables on both sides. And this sometimes poses a challenge to people. It's because it's like, well, where was my variable supposed to be? I only want it on one side. So the trick is to just make that happen. So you'll notice here, if this is like the balance, the teeter-totter, and if I don't want to have x's on both sides, I can simply cut the x off one side, but now my teeter-totter is all off balance. So I'd have to cut the x off of the other side too to balance it. So what that really means is that I could subtract x from both sides. And when we do that, you'll notice that we end up with just 9 left on one side, and then 4 plus, and we'd be left with 2x. And now we have an equation that we could solve in just the way we did before. Another way to think of that, the x is being added to the 9. When it comes across to the other side, it becomes subtract. So that becomes 3x subtract x, which is your 2x if you want to think about it like that. Okay, but this is the why what you're doing is actually working, and there's a diagrammatic approach for that. I'm trying to think, Ian, of the other thing that we were supposed to look at here, distributive property, and Courtney had also asked about long division, wasn't it? Was it Courtney that asked about long division?
I think it was long division that was in there.
It was long division.
Yeah, I was
Sum of
sum of interior and exterior angles, but somebody else was long division. So.
Okay. Let's take a look quickly at long division, and let's do the interior and exterior angles before we go. Okay, so let me find out where I put this here so that I can just find a space to write for us easily. Okay, so I'm not going to have it related to there. You know what? Long division is an algorithm, and it's just a really series of steps. That's why it startles me that this is going to be on your test. But it is, so we can deal with that. So let's say I have the number 5 into 163.4. I don't know. I'm just making something up off the top of my head, okay?
Leanne, just as an editorial comment here, there are lots of things that startle us about this test.
Yes, okay. I completely agree with that. And actually, you know what, you want to know what, guys? This whole long division business, you do it in grade 5, I think, and the next time you do it is in grade 12 to divide algebraic terms. And even then it seems pointless. But anyways, we will do what we do. Here's what I tell my grade 12s when we're teaching this. I use an acronym because really it's an algorithm and it's a series of steps. And so it pains me to just use a process. But they like Dracula must suck blood, DMSB. Something they made up something else with don't something stinky bathrooms, but I can't remember what it is. But we use Dracula must suck blood, and this is the series. This is the cycle of operations that you need to do in order to do long division. And the D stands for divide, the M stands for multiply, the S stands for subtract, and the B stands for bring down. Okay, and we're just going to basically cycle through that process again and again and again. And that's all long division is. So let's try one question together before we move on to the angles. If I want to figure out what 5, and I'm going to look at the 1 to start, and I'm like, uh-oh, 5 won't go into 1. How's that worse? First of all, this is the reason I don't like algorithms, because that 1 is really representing 100, right? It's not 1. But we're going to have to toss that aside if we want to use this algorithm. So I say 5 can't go into 1, but 5 could go in to 16. Okay, so that's my divide component. How many times can 5 divide into 16? And I'm not looking for it to be perfection necessarily. I'm looking for how many times can it fit in. And we know that that would be 3. So that's my division. I've just done the D step. Now I'm going to go on to the M step, which is multiply. And I take this original part of my quotient, multiply it by my divisor, and that's my multiplier. 3 times 5 will give me 15. I've done my M part. Now I'm going to subtract. And I'm going to go 16 minus 15, which is 1. I've done my divide. I've done my multiply. I've done my subtract. And now I notice I can't put 5 into 1. So I'm going to need to bring down another term. So I'm going to use a little arrow there and bring it down. So I'm going to bring down that 3. Now, sometimes you may have seen a little X to bring down. It's probably just habit. I don't use X because eventually I do this division with variables, and that just becomes too confusing if I've got X and time and little X signs. Okay, now we're going to start the process again. So we went through these 4 stages. Now I'm going to go ahead and start back at divide again. So now I'm taking the 5 and seeing about dividing it into the 13. So how many times does 5 divide into 13? It goes in twice. Now I should have mentioned, I'm going to put my decimal right up here, so I keep in mind where that is. So we've done our divide. 5 divided into 13 twice. Now I'm just repeating this cycle. Now I'm at multiplication. So 5 times 2 is going to give us our 10. That's our multiply. Now I'm going to subtract. And when I subtract, I get a 3. So now we've done almost another full cycle. Notice 5 won't go into 3, so I'm going to need to bring down again. So I've got that other number there. I'm going to bring that down, and that's going to give me my 4. Now I'm going to start the cycle again. So can we see that we're just moving through this algorithm, and really that's all it is. We repeat the process. What I should have mentioned is making sure to line up that decimal at the top, and we're just going to kind of keep going. So how many times does 5 divide into 34? Well, it's going to go in 6 times. There's my divide. I'm going to multiply, get 30. I'm going to subtract. I'm going to get 4. And now if I wanted to, of course, we could go ahead and continue to populate more decimals there, right? By having zeros added on the end. And now I'm going to bring this one down, 0, and it actually divides evenly this time, right? and we get 5 times 8 when we multiply. When we subtract again, we get 0. So that ended up actually being a terminating decimal, which is cool, being that it was just off the top of my head.
Leanne, there was just a question there about how do you know where to put the decimal point?
We put the decimal directly above where it is in your devise, in your dividend, right in here. Okay, so, and keep in mind, when I chose where to put that 3, I noticed, well, 5 wouldn't divide into 1, so I didn't put anything above the 1. Notice I didn't put my 3 there, right? Because 5 didn't go into 1. 5 went into what we're pretending is 16. Therefore, I put the 3 above the 6. When you're dividing out here, no, there's not really anything more. No, you're just going to treat it the same way. It's just a hideous type of question if they're going to give you a divisor that's a decimal too. Truly, that's the truth. But no, the real thing to be careful of is right here with that decimal there. I think we should look at some angles and polygons really quickly before we go, if we can. Ian, I'm going to just need to plug in my computer here. It just has suddenly decided to almost die, so I will be 2 seconds, okay?
You go ahead and do that.
Okay. Sorry about that. Sorry about that. I had my iPad plugged in because it was dying, and now that happened. Okay, so let me go back here and let's take a look at exterior angles of a polygon and interior angles, I believe it was. Angles in a polygon. Okay, so something to remember. Are we okay with the sum of the interior angles in a triangle? Is that okay, I think it was Courtney. Yes, we are. Okay, so we know that that's going to be 180 degrees for reasons that if we had more time, it would be wonderful if we could chat about. For the exterior angles, regardless of the shape, it is always going to be 360 degrees. Okay, always going to be 360 degrees. So, see what I have here. So if it's an octagon, a hexagon, whatever it is, that will always be the same. In terms of the angles in a polygon, I'm just finding a good question for us here. Oh, and I've got one for exterior angles as well. Okay, perfect. I'm just making sure I know where we are here. Okay, so are you comfortable with what the formula is for the sum of the interior angles in a polygon? Is that something that it would help us to look at it? A reminder would be great.
Reminder would be great, yeah.
Perfect. Okay. So I'm going to show you what the formula is. I'm going to show you that you don't really need to memorize it because it's actually very intuitive. So the formula is actually the sum of the angles inside a polygon is equal to n minus 2 times 180 degrees. And n actually represents the number of sides in the shape. And I want to show you why this formula is the way it is. So obviously, if I have a triangle, there are 3 sides in the triangle. There's one triangle, obviously, and there's 180 degrees because we established that we knew that. If I had a quadrilateral, I don't care if it's a rhombus, I don't care if it's a parallelogram or if it's a square, it's going to have 4 sides. And if I try to join my diagonals and say, how many triangles can I make inside of that? I don't care how I draw my diagonal, whether I draw it from left to right or whether I draw it from right to left, doesn't really matter. I'm always going to make only 2 triangles. And notice we know that there are 180 degrees in one triangle. So if my shape contains 2 triangles, then I actually have 2 times 180 or 360 degrees inside that shape. If I have a pentagon is a 5-sided shape. I could similarly choose one of the vertices and just say, how many triangles can I draw? Now I'm doing this quickly for you, but you could try. It doesn't really matter which of these vertices or corners I start at. I'm going to use one of them and say, how many can I draw? And it's not syncing with me, but I've drawn another one here. We'll notice if we have a 5-sided shape, I actually have 3 triangles. So that becomes 3 times 180. And similarly with the hexagon. So if I were to draw a 6-sided shape, we notice that 6 sides, I have 4 triangles. And if I wanted to find the sum, I get 4 times 180. So if I were to extend that and I had n sides in my shape, an n-gon or a polygon with n, so any number of shapes, it's always, notice the number of triangles is always 2 less than the number of sides in our shape. So it's really n minus 2. And then that gives us the number of triangles. And I times that by 180 degrees. So that's a way that it's easy to remember. So I actually say, okay, if I had 100 sides, I've got 98 triangles times 180. I mean, I don't think you're going to get an n-gon or 100-sided bigger, but that's the idea, that we could extend it that much. So let's take a look at how we would actually use this type of scenario. So there's an interior and an exterior angle example here, thankfully. So here is, we are given, a number of different angles inside this polygon, and there's one that we don't know, and we're asked to find that unknown angle. So the first thing I want to know is, what do all of these angles actually add up to give us? So I'm going to count the sides. I've got 1, 2, 3, 4, 5, 6 sides. So that's the first important piece of information that I would need to have. If I've got 6 sides, that means that I could possibly make 4 triangles inside that shape. I know that each of those 4 triangles have 180 degrees in them. And what's that going to give me? 720? Which is 720 degrees in total. Now, if I didn't like that, if I'm a person that really likes formulas, then by all means, memorize the formula. We said n represented the number of sides. Notice that I just plop in the 6 for the n. And that gives me 4 times 180, which is the exact same thing that we got just thinking through it in a logical way. Now, if I wanted to find that a, if I know that all of these added to give 720, I could find a by simply taking 720 and subtracting these, right? Because I know that whatever's missing here needs to add to all of these to make up the total of 720 that we know should be there. Is that okay? It is magic. It's mathemagic. You're welcome. So in this scenario, I'm looking now, I was thinking it was an exterior angle one. It looks like it's probably more interior. The second example, because I also have an interior angle that's missing. So notice, if I wanted to solve in this scenario, I would actually have to use this exterior angle to find out what this interior angle was. And now I would only be missing one of these interior angles, and I could go forward from there. Are we okay with what the connection is between an exterior angle and an interior angle? Yeah, because it really, these angles are what we call supplementary, meaning they add to 180. So if I wanted to find this missing angle C, I could take 180 degrees minus 102, right? And I could get angle C. And then basically we would just repeat the process that we did over here on the left side. The only difference is we might need to do some calculations again to figure out what the sum of the interior angles would be here, because there's 1, 2, 3, 4, 5 sides. So the big takeaway for this is that if it's interior angles, yeah, we can look at that one. If it's interior angles, it changes what those sums are. Okay, you've got to figure out how many triangles and go through that. If it's exterior angles, it never changes. That's the easy one because they're always 360. And again, take a look at the Desmos for that because I actually created something that shrinks a whole bunch of different shapes and you can visualize it actually becoming 360 regardless of the number of sides. Okay, so we can do this one. We just got asked, can we actually finish this one on the right here? Okay, so let's find angle C. We noticed that we would go 180 minus 102 degrees because they're supplementary, otherwise because they're a straight line. So what's that? My brain, 78 degrees. So we know that this is 78 degrees. Now we still need to find that angle B. That's another interior angle that we don't know. But we don't know what these angles inside would add up to. So we would need to find the sum of that interior angle shape. So we notice there's 1, 2, 3, 4, 5 sides. So 5 sides, which means there are 3 triangles, which means that there would be 3 times 180. What's that, 540? It's been a long day. Okay, would be 540 degrees. And then from there, if you wanted to find angle B, you would take the 540 degrees and then subtract the other angles that are provided there. Whoopsie daisy. And we would get our answer that way. Sorry, guys, it's not showing you the whole thing at the top. Good luck, everybody.